Hey, this is a PowerPoint about conducting a science experiment that would ultimately go to a science fair. This is very important because you've been picking questions and formulating hypotheses, and planning out experiments. And next, really, I'd like for you to actually do the experiment. So this is both a review and kind of push ahead to how you would conduct an experiment. It's called Science Fair Planning Guide. From this point forward, you are now a scientist. It starts here. Here's the scientific method. Let's look at the first one. Find a problem, ask a how does question. You've already done that. Research the problem and find out all you can. Create a notebook. I don't know if you've done this part yet. Taking the research that you found and putting it in a notebook, including the links and the titles and authors and all that stuff too. Make a hypothesis, predict what you think might happen based on your research or your prior knowledge and your experience with the items in your experiment. Conduct the experiment to find out if you were right. Test, test, test. Here they don't have the step in here where it talks about writing out the plan or the procedure. The reason you write it out is to make sure you're not forgetting anything, to make sure you've got all the ingredients like a recipe, to make sure you've thought out every step, to keep it consistent. Remember, you keep it consistent to make sure that the results aren't based on something crazy and from left field. Like if you do the experiment 2 or 3 different ways, 2 or 3 different times, well, you're not sure what got the result. Was it, one variable or another variable? You want to keep it very, very consistent, the same each time. You conduct it, and you compile proof by recording data. This is what this PowerPoint's going to talk about. Organize your data into tables and graphs. We'll talk about that later. Form a conclusion. Check your hypothesis against the results you got. Were you right? And then you write about what you learned and how it applies to the world. Getting started, what you need. You need a science notebook. It's like a journal. It can take any form. It can be stapled paper. It can be an actual notebook, spiral bound. It's up to you. It's important if you're going to have it over a long period of time. You can put diagrams, drawings, pictures, notes, questions. You write it all down in the notebook. Having the right tools to do the job. Make sure that the materials you need, you take accurate measurements, like with a ruler, tape measure, thermometer, and make sure those tools are operational. Sometimes if you borrow old stuff from people, they don't work. So make sure it's, you test it on other stuff before you use it, let's say. Keep a science notebook. Good entries include the date. If you're doing an experiment over a week, which is, recommended, you're going to put the date each day. Drawings, accurate pictures. Now we have cell phones. You can take cell phone pictures if you want. Labels and or descriptions. Questions that you have. I noticed statements. I observed, I learned, I discovered. And then I wonder statements. If you notice something, hopefully it also clicks in your head and makes you wonder, well, if that happened, then why? Or where did that come from? So all of that goes in your science notebook. Next, it says what a real science notebook looks like. Reference graphs and tables pasted into the notebook. So that's something to consider too. You don't have to have everything start originally in the notebook. This can be a spot where everything goes. If you have to print something out or if you have to create it on something else, it can all just be pasted into the notebook. But it does have graphs, it has observations, it has, look, this guy has formulas in here. So it all goes in there, and try hard to keep it organized. Hey, this shows you how to keep it organized. Table of contents. The first page should always be your table of contents. And you're slowly building your table of contents as you consistently put stuff in. So you would put the date, the activity, and then the page number that they'll find that on. Number your pages so that the table of contents makes sense. Add the date at the top of each page that you are working in. Notebook contents. Observation organizer. You can make it this way if it makes sense to you. Tables, as I've become an adult, I've given up, and I've realized that tables will keep me organized. So a lot of times I make tables. I'll do it in PowerPoint or I'll do it in Microsoft Word. when I was building your course. I made a lot of tables so it was clear and easy to see. So I hope when you're making your science notebook, you incorporate tables like this, because it'll help me when I'm reading through all your stuff. You've got a compare and contrast table notebook here for your notebook, and it gives you even sentence frames to help you. This is just to help you. Project resources. It talks about the stuff you can use to research. I know you already researched, but if there are further questions, you might want to go back and see if you can find if somebody else did your experiment and what steps did they take and what did they find. So it talks about using the internet, magazines, your environment. This is what I talked about earlier. You might have some research that you've just done by living, prior knowledge, your experience with things. Oh, look, that's the next one, your experiences. Those help guide your decision making in making an experiment and conducting an experiment. And then also other science fair projects. I'm perfectly comfortable with you looking up what other people did and seeing how that compared to what you've done. Remember, do not simply redo the very same experiment you found. I like that. You need to be creative, change it, and make it your own. Judges like projects that show creativity and different thinking. This is talking about submitting it to a science fair. Your question should be about something you are truly interested in finding out. So you can take anyone's experiment and twist it and make it your own. There's going to be an example in here of what somebody decided to do for theirs. I'll show you right here. It says, John watches his grandmother bake bread. He asks his grandmother what makes the bread rise. She explains that yeast releases a gas as it feeds on sugar. John wonders, remember we talked about that, if the amount of sugar used in the recipe will affect the size of the bread loaf. So you can see where he's already formulating a science fair question. Do the research. My problem is about blah, 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 blah subject. See, they say magnetism or electricity, absorbency, taste, plant growth, or other scientific topics that relate to your problem. If you're having trouble finding out what topic it is, ask your teacher or an adult. That's good advice. Remember to use more than one source. Write your research sources in your notebook. Also write notes about your research, about your paper in your notebook. Use different pages for each source. And it gives you an example of how you could put that in your science notebook to make sure you're clear to tell that what book you got, what the author was, and the notes you found from it, or what the internet site was and the notes you found from it. Research plan. I liked this. I know we did research already, but I know sometimes when you're digging deep into a tough question, you might need to do more. Background research is necessary so that you know how to design and understand your experiment. To make a background research plan, a roadmap of the research questions you need to answer. Follow these steps. Identify the keywords in the question for your research fair project, science fair project. Brainstorm additional keywords and concepts. Use a table. Table came up again with the question words why, how, who, what, when, where to generate research questions from your keywords. For example, what is the difference between a series and a parallel circuit? When does a plant grow the most during the day or night? Where is the focal point of a lens? How does a Java applet work? Ooh, that's a computer one. Does a truss make a bridge stronger? Why are moths attracted to light? Which cleaning product kills the most bacteria? Throw out the irrelevant questions. Irrelevant means they do not matter. They are less important than the other ones. Research plan. You should also plan to do background research on the history of similar experiments or inventions. We talked about that. So that you can design an experiment, you need to research what techniques and equipment might be best for investigating your topic. This will help you find the tools you need to do it, and to do it accurately and consistently. Rather than starting from scratch, savvy investigators, really smart, witty, ones that don't want to work too hard, want to use their library and internet research to help them find the best way to do things. You want to learn from the experiences of others rather than blunder, mess up around, and repeat their mistakes. So that's really good advice. Background research is also important to help you understand the theory behind your experiment. In other words, science fair judges like to see that you understand why your experiment turned out the way it did. or does. You do library and internet research so that you can make a prediction of what will occur in your experiment, and then, whether that prediction is right or wrong, you will have the knowledge to understand what caused the behavior you observed. So you need to kind of be an expert in your subject. All this research stuff will help you at the very end when you get your results. You've done enough research to understand, oh, that's why I got that result. That's the idea of doing the research. Now we're going back to John. John researches I like this little meme here. John researches the areas of baking, or rather, that's a GIF. The areas of baking and fermentation, and tries to come up with a way to test his question. He keeps all his information on this topic in a notebook. After talking with his teacher and conducting further research, John comes up with a hypothesis. If more sugar is added, then the bread will rise higher. So he knows the elements involved. He knows the variables. We talked about that earlier in this folder. So he chose to change the variable of the sugar to see what that does for the result, the cause and the effect. Write a procedure. You've done this. Now, I kept this slide because I don't know that you know this. As you're doing an experiment, it says, did we mention to take pictures of yourself doing the steps? And the importance of taking good notes in your notebook. Please take pictures. Don't just take pictures of you smiling next to a test tube, but rather, I want to see the actual experiment. Back to John. The independent or manipulated variable, changed variable, is a factor that's intentionally varied. It's intentionally changed by the experimenter. John is going to use 25 grams, 50 grams, 100 grams, 250 grams, 500 grams of sugar in his experiment. So he's going to do his experiment at least 1, 2, 3, 4, 5 times. Consider that as you're doing your experiment. How many times will it take to prove what you're trying to prove? Hopefully it takes over the course of a week, or it's multiple trials the way John is doing. The dependent or responding variable is the factor that may change as a result of the changes made in the independent variable. In this case, it would be the size of the loaf of bread. So the independent variable was the sugar, and the dependent variable is supposed to change. That's his plan. He thinks that it's going, every time he puts a different amount of sugar in, the dependent variable should be the size of the bread, how tall it gets. And so he would measure that and put that in his notebook. Remember, as you're making yours, what's the independent variable, what's the dependent variable? Then what tools are you going to use to measure the dependent variable? Keep going with John. John's teacher helps him come up with a procedure, list of directions, and a list of needed materials. You've done that. She discusses with John how to determine the control group. It's going to go into control group now, and I'm pretty sure you know about this. Let's see. In a scientific experiment, the control group is the one that serves as the standard of comparison. The control group may be a no treatment or an experimenter-selected group. The control group is exposed to the same conditions as the environmental group, except for the variable being tested. All experiments should have a control group. So if you need help figuring out what your control group would be in your experiment, please email me or call me. And if I can't help you, I sit in an office with middle and high school teachers. I have a science teacher that sits 2 desks away from me. He can help me help you come up with a really good control group. And that can really prove your point and make your hypothesis even stronger if you have a solid control group. Let's go back to John. Because his grandmother always uses 50 grams of sugar in her recipe, John is going to use that amount as his control group. John's teacher reminds him to keep all other factors the same so that any observed changes in the bread can be attributed to the variation in the amount of sugar. So John's teacher is reminding him not to change any of the other ingredients. Don't add more water in one and less water in another, or more flour or anything else. Only change the sugar. Everything else is the same measurements. That way, when the bread does rise more with a certain amount of sugar, then you can go, well, obviously it's the sugar that caused that. Constants. The constants in the experiment are all the factors that the experimenter attempts to keep the same. The flour, the water, the yeast, you keep it all the same. I gave it away. John's constants might include other ingredients in the bread recipe. Oven used. He's not going to use multiple ovens. He's going to use the same exact oven that gives across the same exact heat. The rise time. How long does he keep the bread in the oven? Brand of ingredients. Cooking time. Type of pan used. Air temperature and humidity. Where the bread was rising. Oven temperature and age of the yeast. He's keeping it all the same. John writes out his procedure for his experiment along with a materials list in his journal. He has both of these checked by his teacher where she checks for any safety concerns. And you already turned yours in to me, so that's perfect. Test, test, test. Remember, the judges expect your results to be consistent in order to be a good experiment. In other words, when you cook from a recipe, you expect the outcomes to be the same if you followed the directions or procedure step by step. So that means you need to do the experiment more than once in order to test it properly. We recommend 5 times or more. More is better. Confirm the results by retesting. So you're going to, like I talked about before, do your experiment over and over, and that way it'll prove it even more. Don't forget to take pictures of the science project being done and the results. Write about each test and what happened in your notebook. So you've got your observations next to the pictures or next to the diagrams or the sketches. Or you might need to add your pictures later. But, each time you're labeling it with a date, labeling it with a trial, and be very, very specific so at the end you're not confused. What was this a picture of? I can't remember. When I've done science experiments before, I've put a little notebook card in front of the, let's say, the bread, and I might write 50 grams of sugar and have a ruler next to how tall the bread turned out to be to show it in the picture. And not even show the amount of sugar in the bread because you can't see that with your eyes. You need a label. Back to John. Trials refer to replicate groups that are exposed to the same conditions in an experiment. John is going to test each sugar variable 3 times. So I think he's making 15 loaves of bread. Hopefully he can share it with his class when he's done. Collect your data. This means write down or record the results of your experiment every time you test it. You also need to organize it in a way that's easy to read the results. Most scientists use tables, we talked about that, graphs, and other organizers to show the results. Organizing makes the results easy to read and much easier to recognize patterns that might be occurring in your results. Besides, it impresses the judges when you use them. But don't make a graph or table because we asked you to. Use it to benefit your project and to help you make sense of the results. There is nothing worse than having graphs and tables that have nothing to do with answering the question of the science project. Label your graph. How do you collect data? Tables, charts, and diagrams are generally the way a good scientist like you would keep track of your experimental trials. A table is organized into columns and rows and always has labels and headings telling what the columns or rows mean. You will probably need a row for every time you did the experiment and a column telling what the independent variable was, what you tested, and the responding variable, the result that happened because of the independent variable. This will be complicated. I am available to set up tutoring online or face-to-face, depending on how we could schedule it, and I will help you take all the notes and all the data you collected in your notebook and turn it into a table or a diagram. You're going to be asked to turn in at least one table or one chart to track your data. If you are uncomfortable with that, I completely understand, and I will help you take all those good notes you collect and put it into a table or a chart. So keep that in mind. It says, be accurate and neat. When you are writing your tables and charts, please make sure that you record your data in the correct column or row so that, that you write neatly, and most of all, that you record your data as soon as you collect it so you don't forget what happened. Sometimes an experiment might be hard to explain with just a table. So, if you have to draw and label a diagram or picture to explain what happened, it is recommended that you do. All right. It says use the right graph for your experiment, and this is tricky. Again, if you need help, please let me know. There's nothing worse than a bad graph. There are all types of graph designs, but these seem to be easy to use for science fair experiments. Pie graphs are good to use if you are showing percentages of groups. Remember that you can have more than 100%, and all the pieces you can't have more than 100%. I misread that, I apologize. And all the pieces need to add up to 100%. This type of graph is great if you are doing surveys. Surveys are something you could add to your experiment. Bar graphs are good to use if you are comparing amounts of things because the bars show those amounts in an easy-to-read way. This way, the judges will be able to tell your results at a glance. Usually the bars go up and down. The x-axis, or horizontal axis, is where you label what is being measured, like plant A, B, C, and D. And the y-axis, or vertical axis, is labeled to show the unit being measured. In this case, it would be centimeters that the plant grew. So that's bar graph. Last is line graph. Line graphs are good to use if you are if you are showing how changes occurred in your experiments over time. In this particular case, you would be using the x-axis to show the time increments, minutes, hours, days, weeks, months. And then you'd use the y-axis to show what you were measuring at that point in time. And then these are examples. It has plant A, amount of water per day, none. Size it grew, 0.5 centimeters. Plant B got 5 milliliters of water and it grew 2 centimeters. So they're tracking it using a table. This is line graph, this is pie graph, this is a bar graph. You can take a table that you kept in your notebook and turn it into a bar graph pretty easily. I can even show you how to do it on the computer, and then it does the work for you. Plant A was 0.5 centimeters, if you remember. Plant B was up to 2 centimeters. And then it shows the axis here and the axis here. Data analysis. This includes a paragraph analyzing or explaining the results of your data. What happened? What pieces of data were interesting to you? Did anything not go as you expected? This is a valuable paragraph. This is going to be worth a lot of points. I do not expect that your experiment will go 100% according to plan, and you will absolutely prove your hypothesis. That generally does not happen. Scientists have to do different types of experiments, and they have to alter their experiment over and over again because they think something will happen and then it doesn't. What I want to know is what didn't go as planned, and then also I want to know why do you think it didn't go as planned. You might have to go back and read up a little bit more on your topic, or you might have to go back and read up on your procedure and see if there's some variable you did not control. So if you didn't get the results you expected, maybe it was because the variables kept changing and you can't figure out if it was variable A or variable B that caused the result. So this is a very, very, very helpful paragraph that I hope to see you do a really good job on. This is back to John. John comes up with a table he can use to record his data. John gets all his materials together and carries out his experiment. And then you see, this is a good chart. The amount of sugar, remember he talked about changing the grams, the size of bread loaf number 1, the size of bread loaf number 2, and the size of bread loaf number 3. And then what he did to make it easier on himself is he got an average. He added these 3 numbers up and divided by 3, and the average was this. So he can just compare these numbers. He doesn't have to compare all of these numbers. And so 50 grams of sugar was $13.44. Then 60 grams of sugar is $13.80, so it went up a little bit, then it goes up a little bit when you increase the sugar, then it goes down, then it goes down. So I'm not sure what he's going to come up with as his analysis at the end. That's interesting, because the sugar keeps going up, but the size of the bread goes up, 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 back down, 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 down. Maybe there's an optimal amount of sugar in the middle. You'll stick with 70 grams and you'll get your tallest, the largest bread, I guess? Conclusion. The conclusion is where you tell us what happened. I did this experiment, I did this way, and this is the results. Was your hypothesis right or wrong? Or neither? Were you successful? Did it turn out okay? Would you change anything about the experiment, or are you curious about something else now that you've completed your experiment? And most of all, tell what you learned from doing the experiment. Feel comfortable telling us that the experiment didn't work, or that you're curious if you changed these certain things in your experiment, would you get a different result? I'm not going to expect that you do another science fair experiment. You just have to do one. So you can kind of use your pretend brain and say, in pretend world, but don't write it this way, I would do this experiment over again and I would do it this way because I'm curious about whether that would change my results. So feel comfortable acting as if you were going to do the experiment one more time. I won't make you do that though. Let's practice. We're going to go back to John. John finds that 70 grams of sugar produces the largest loaf. His hypothesis is accepted. So I guess maybe just increasing the sugar increases the size of the loaf, and you just decided not to pay attention to the end of the chart? Maybe? I don't know. These are some good websites that can help you conduct your science fair experiment better. So I'm going to attach this PowerPoint to this assignment if you want to refer to these websites, or copy them down. They're long though, so just open up the PowerPoint and click from there. The end. I hope that helped. If you need help, remember to contact me because I'm here. I'll help. I like helping. Good luck.